So in this lab, we're going to be looking at some more topics related to simple regression models, or a little more advanced regression models. So let's say this is lab 3, and we'll call it more regression. And this is associated with lecture 3. So we had, let's make this a little bit smaller. Okay. That work? Okay. So last time we had left off, in the last lab, we had loaded this mass library, and we had loaded this Boston data set. And if we looked at the Boston data set, if you recall, it contains data on housing values in the suburbs of Boston. And in particular, this value med B is the median home price, and we looked at predicting that from crime rate. And so what we had done last time was we had built a model using LM, which is basically how you fit regressions in R. Stands for linear model, and we said that we wanted the median home value to be predicted from the crime rate. So we had used this kind of weird formula where we said, thing we want to predict tilde crime, the predictor variable. And so we had done this, and we had said the data is the Boston data set, and we could ask maybe for a summary of our model. So when we run that, we get our estimated coefficients, for example. And we had seen, for example, we could get the predicted values, maybe call them y hat, by calling the function pred on the model. That would give us y hat, and for example, we could plot the crime rate against the predicted median value, hopefully. Oh, maybe I need it. It should be predict. So this was the trend. So this is on the x-axis. Here we have the true crime rate of each of these suburbs, and on the y-axis we have our predicted crime rate. And it's linear, right? It's linear with our intercept at 24, so at a slope of negative 0.4. And this model is okay, but we had seen that when we had plotted the data. So if we plotted crime on the x-axis against the median home value on the y-axis, it looks something like this, and it wasn't particularly a very linear trend. And so when if we plotted our regression, maybe we'll make the line red. It's okay, but it's not a really great summary because this trend isn't particularly linear, even though our regression line assumes it has to be linear. So one thing we can talk about is we can talk about covariate transformations. And so we can do that if we say we want to build a second model, and we want to again predict the median home value, but now we want to predict it from maybe we want to predict it from the log of the crime rate, and indeed maybe we want to predict the log of the median home value, right? Because we had seen there, so let's back up here, we had seen that if we plotted log of crime rate against log of the median home value, we got something that at least wasn't weirdly censored in these same ways, and so maybe it looks a little bit better, and maybe you believe that you could linearly summarize this trend a bit better. So we could build a second model, and all I'm doing is I'm just passing for the logarithm. I'm just adding in log to this side of the equation here and log to this side, and then I should tell it that my data is the Boston data set. So we could fit that, and we could look for a summary of this thing. It's obviously it's going to have different coefficients, not surprisingly, because because it's different. You know, the y's and the x's are different in this case. But we could again, maybe if I copy this here, we might believe now in this case, if we plot, let's try this. Oh, why is it giving me an error? There we go. Then maybe that's actually a more reasonable model to build. So linear regression is going to run whatever you tell it to, but it's not going to, think really hard about whether or not that's the correct thing to do. So it's pretty easy to include these covariate transformations. For example, I can include them, just apply the function in the LM function. That works for some things. So let's just let's try some other kind of covariate transformation. So let's just say log med v is log of the median value, and let's say that let's call the transformed crime as the log of the crime rate. Because I pulled these out as individual variables, I now, when I call LM, transform crime, I don't actually need to specify the data argument, right? Because these are just variables. Let's call this mod3, right? So this should be the same exact model that we just fit. Okay, and those are the coefficients. And my claim was before that all we need to do to get these beta hats is to form the, all that this regression function is doing behind the scenes is getting the model matrix, and forming x transpose x inverse x transpose y, right? So if we make this thing, let's just make sure it's an array of the right size. So now this is 506 rows, 1 column, and I can get the model matrix from my model, call it x, and you can see what the model matrix is. We could have written it ourselves, but you can actually just grab it from the model itself with model of that matrix. There's ones down that first column, and then it has my transformed crime rate. So here's the first couple of values, and indeed, if I look at log of Boston crime, just look at the first couple of those values. Indeed, it's just transforming these x's here. These are exactly the same. And so I can get beta hat as by forming x transpose x inverse x transpose y. So it's x transpose x, so that's transpose x times x. I want to invert that, so x transpose x inverse multiplied by x transpose multiplied by y. So t here is my transposition operator. Of course, it's not called y, is it? What did we call it? We called it log med value. And if I look at beta hat in this case, it is 2.95 negative 1.07. Does that match? Here's the moment of truth, actually, so we can get. Nope, that's not the right mod. Mod 3, right? So mod 3 was the model we had fit up here, right? Log, that's log, and that's 2.95 negative 1.07, right? So it indeed gets it right. And all that my design matrix is in this case is just literally one set in the first column and then my transformed variables here. And if I wanted to change this, so maybe I think that, so let's just add something in here. Maybe I want to test out a different kind of transformation. So I want to leave y as a log of the median home value, but maybe I want to try the square root of the crime rate. So let's look at that, what that looks like. Yeah, it's not great, but I'm not that smart, so I'm going to try this out. I could, if I were to instead do the square root here, I could rebuild this all. I'm going to get different beta hats, but if I look now at my model matrix, these values are now, all that's changed in the model matrix is now it's the square root. So probably not a great idea. We can undo some of this, right? I'll change it back to log. But, you know, variable transformations are really easy to include in my regression model because all I need to do, and all that really LM is doing behind the scenes here, right? When I call LM here, all it's doing is transforming the column of my model matrix here. So it's very easy. If I wanted to work with a square, I wanted to work with something else, it's very easy to include these transformations using LM. Another thing that we wanted to talk about was categorical variables. So let me put a heading here. What do we want to do? This is transformations. So let's say variable transformation. I'll make that markdown and we'll format it. We also want to talk about categorical variables. So we're going to switch data sets here, and we're going to work with a data set called birth weight. That's, of course, not how you spell birth. Let's try spelling it right. Okay, right. So birth weight, we can get some information on it. So with the question mark. And so it has a bunch of covariates here. One of them being race. And race is encoded as 1 for white, 2 for black, and 3 for other. So we look at, so let's just look at the first couple columns of this data set, right? So here we have other things like smoking habits and things like that. And so here's our race column, and you can see it's an integer, and it's just numbers. So if I look at the first couple values of race, it's numeric. And so the problem is that we don't want to treat this as numeric, because it's not like there's not a numeric relationship. It's not like other is 3 times white. Doesn't make any sense. You can't multiply these things. You can't add them. They're just number labels. So the proper way to deal with this in R is to use a factor. And so let's call this race F factor. And so let's just look at the first couple of these. Okay, so if we don't do anything, it's just going to be a number. We want to make it a factor, which is R's way of denoting a categorical variable. And we can make it a factor by calling as.factor. And if we do this now, when you print it out, it comes up with this thing that says levels, 1, 2, and 3. And so when it prints that out, you know it's a factor, and it's not just a number in this case. And of course, but it still has these kind of weird labels that aren't really meaningful to us. We can rename the levels of the factor by using the function levels. So let's say levels of race f, and we want them to be what? So 1 denotes white, 2 denotes black, and 3 denotes other. And so now if we say maybe print out the first couple values of race f, now instead of just numbers, it's actually meaningful. Black, other, white, 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 other. And again, we can see that the levels here are white, black, and other. So this is the proper way to deal with it. If we don't do this, then LM is going to think that race is a numerical variable, and it's going to think it can do kind of normal arithmetic on it, and it's going to be confused. So if we want to build a model with this, for instance, maybe we want to predict birth weight from race. First of all, we should modify this birth weight. Oh, nope, don't do that. Back. We should modify race so that it's not a factor version, and then we can build it using LM in a kind of classic way, but now it's going to deal with it correctly. So let's do that, and then we'll print out a summary. I can't spell birth, which is an issue, and there we go. And so when you do this, you see that it's gonna have coefficients associated with other and black. You don't see white here because that is the so-called the base category for this categorical. So the way you interpret this black coefficient is that this is the difference between white and black. And the way you interpret the race coefficient is the difference between white and other. So sorry, race black, the coefficient here is the difference between white and black. Race other is the difference between white and other. And the intercept is basically the base case, which assumes white. There are ways you can do this when you mess around with factors. You can change the base levels, you can re-level it, you can do all sorts of fancy things, but this is just the standard way it's encoded. So you always notice if there are k levels, in this case we have 3 levels for a factor, there are 3 minus 1 is 2 levels for our coefficients here. We can get our model matrix, we can look at what that looks like. So I can say model matrix mod, let's just pull the first couple rows. And you notice that I have k minus 1, 2 dummy variables associated with my race categorical variable. So I've basically taken this categorical variable that isn't numerical and I've encoded it as 2 dummy variables. And of course I have my intercept column there too. So that's some of the basics of how to deal with variable transformations and how to deal with categorical variables for linear models when fitting these things. So I think that's probably a good place, and we can stop there.